Okay, so yeah, we can start. So last time we had a long discussion where we introduced the ideas of forces and Newton's laws. So we looked at several properties. We looked at the law of inertia. We looked at F is equals to ma. We looked at what friction is and also what the normal is and its behavior. Now the questions that we're going to look at, we're going to do some of these, but I will eventually also create a recording or recordings for whatever that will not work out together in the online classes. So I'll pick maybe one or two or three for tonight. Then maybe tomorrow night also do a few more. But then come next week, we're going to move on and start looking at work, energy, and power. So that is the idea, and that is how we are going to proceed. Okay, so yeah, having gone through the what we did yesterday, do you guys have questions based on what we did? Do you have any questions from what we did last time? Okay, so let's proceed. So now this is all going to be about question, so that you guys hopefully get to have a good idea of what is actually happening here. So let's look at the first question here. In the first question, we're being told what? Two horizontal forces act on a 2 kg chopping block that can slide over a frictionless counter, which lies in the XY plane. One force is this and that. Find the acceleration of the chopping block in unit vector notation when the other force is this, that's F2, and then B when the other force is that, and then C when the other force is that. Now, the first thing that we want to understand is this notation that they are using. It's perhaps among the things that we didn't look at last time. F1 here, the vector F1 is being given as 3.0 newtons I plus 4.0 newtons J. And then we have those funny hats there. Now, the question that we have is, before we even understand what the question is, what does this notation actually represent? We looked at forces last night. We saw what they are and also how to handle them, but we didn't necessarily look at this notation. So what does it imply? Well, this is what we call the Cartesian vector form. It's a way of representing a vector in terms of its components. So I'm saying it's general for vectors. It's not only for force vectors. It can even be used for displacement vectors. Now, how does it work? Well, you look at the XY axis. In this case, you guys deal with two-dimensional coordinate axis, with your Y-axis being here and your X-axis being here. Now, here, of course, you know to say your X component is going to be the piece of the vector that runs like this. Like, for example, take a vector that is, take a vector like this one. Let's say this is where F1 is. Say you have a vector here, F1, and I'll put a bar here to just mean that this is a vector. Now, you know to say, if you know what the angle here is, you can easily find the components of that vector. For now, this is just vectors. It's not even forces yet. So if you know what the angle here is, you can easily get the X component of F1. And you can also get the Y component of F1. So I can even come back and say, this is F1 in the X-axis, and this is F1 in the Y-axis. Now, when you find F1, it will just be a number, maybe 5 newtons. I'm just saying maybe because I'm just putting a number there. Even when you find y, the y component, it will also just be a number. Let's say maybe 4 newtons. Let me say this one is a 3. Let's say that is a 3 and that is a 4. And these are forces. The components are also forces. So we expect them to have the correct unit for force. Okay. With that in mind, the Cartesian vector form of representing the forces, it's more like you want to combine them, but you're not really just going to take that, to use Pythagoras theorem to get the final answer. When it comes to expressing a vector in Cartesian vector form, all you have to do here is, like for example, a vector in this case, since you're in the x and y, it will be made up of 2 components. The x component, fx, and the y component, fy. But instead of just adding them or writing them like this, we have to show their direction, because this is just a number here, and the other one there is also just a number there. Okay, so sorry for that. Okay, so I was saying that these are just numbers. But if you're going to represent these numbers in Cartesian vector form, you also want to just show to say that when you find this fy, it is in the x-axis. Now this fx, it is in the x-axis. And then you write this fy, you also just want to show that this is a y component. So how do you then do that? Well, it follows that you can write this first vector f1 as just the x component of f1, but to indicate the direction that the fx is actually in the x-axis, what you do, or what is done here, is that these directions, the x-axis, its direction is noted or denoted by a unit vector I. So I means you are in the x-axis. It's just a unit vector, something that is used to illustrate direction, or to just tell us to say, okay, it's in this direction. Here as well, in the y-axis, the unit vector that will be used there is a unit vector j. So this unit vector as well is just there to tell us to say that, okay, when I write 4j, I mean it's 4, the magnitude, and then j to mean in the y-axis. So here, for example, we had fx, so I can say fx and also fy. But to just point out that this is actually in the x or in the y, we'll say that, okay, this is actually in the x-axis and this is in the y-axis. So again, a question that most students here will ask to say is that, if we wrote fx here, then why are we writing I as well? Doesn't fx mean that we are in the x-axis? Well, it does. But look at what fx represents. When I wrote fx here, I said fx is equals to 3. So fx will be the magnitude 3. It will be part of what gives us that 3. The x is not telling us the direction. It's just telling us that the x component is 3. But to remain giving the direction, when I put a 3 where there is that fx, I still need to know that this is actually in the x-axis. That is where that I actually comes in. Okay, so I hope you've got that. Okay, so yeah, basically this is how it goes. Then even for the y component, here the y component, I said it's a 4. So we can come and write this as a 4j. So the first f1 can then be written, not that. The first f1 can then be written as a vector which has 3i plus 4j. So this is the first vector f1 in Cartesian vector form. Now, with this description, I want you guys to see what it then means. Look at the one that they gave us, this one here. What does it then represent? Well, when you look at this first vector here now, it should be clear to you what these values represent. For example, when you look at this 3 Newton, and then we have an I here, it's like they are actually giving us the component. In most cases, they'll give you the force vector itself, F1, and then give you an angle. Then you'd have to get what the components are. But in this case, weird as it might look, it's actually easier to deal with forces like this because they are actually giving us the components in advance. What they're telling us is that the x component of F1 is actually 3 newtons, and the y component of F1 is actually 4 newtons. Why saying that? Based on the unit vectors. This is I, meaning the 3 is in the x-axis, and this is J, meaning the 4 is in the y-axis. If we had the third axis here, the z-axis, we would have seen something like plus, maybe something here for F1 in the z-axis, and the unit vector used there would have been a k. So this is how they would have represented the third axis if it was present. But to a large extent, you guys will be dealing with only 2 axes, so you might only have these 2. Okay, having described what the Cartesian vector form represents and means, I think we are now ready to move on to the next part, which is to actually answer the question. Now, let me ask you guys, how would you find the magnitude of the force F1? If the question was, find the vector or the force F1. This is the Cartesian vector form. What if they wanted you to find the force vector F1? How would you find it? How do you find F1? Yeah?
Maybe by the Pythagoras theorem.
Exactly. So like I pointed out earlier on, these are components of the force F1. And since they are both positive, so if I was to do something like this, it's like we have the x component as a 3, just like I showed earlier on. This is a 3, and the y component is a positive 4. So you have a positive 4 here. So the vector itself, F1, it has to be a force vector starting from here, ending where the y component ends. This is where F1 is. And clearly, if this is 3 and this is 4, we see this is right angled. So meaning F1 magnitude will be equal to the square root of 3 squared plus 4 squared, and then this would be equals to 5 newtons. So this is the magnitude of the vector itself, but that is if we need it. For now, I just wanted to make sure that you understand how the different ways you can interpret that statement. Okay, now we can go to our question and try to answer the question. 2 horizontal forces. So 2 horizontal forces, okay? Now, a funny thing, the statement is telling us that these 2 forces are horizontal, meaning they are literally on the horizontal axis. And then what else? Act on a 2 kg chopping block that can slide over a frictionless kitchen counter, which lies in the XY plane. One force is this. Find the acceleration of the chopping block in unit vector form. So see again, they're saying unit vector form. So they are calling it unit vector notation. It's the same as what I was calling the Cartesian vector form. It's just this form of representing these components in terms of their unit vectors, as in leaving your answer in this form. So this is what they just mean here. Okay, so they want us to find the acceleration. Now, before we look at that acceleration, before we get there, remember what we did last time? We find the acceleration using Newton's second law. So question 1, solution. So here we're going to use Newton's second law. We're looking for acceleration. We're given forces. Are we given the mass here? Yes, we're given the mass. They are acting on a 2 kg chopping block. So what is happening there? Well, in this case, we have Newton's second law states that, from Newton's second law, we get the sum of the forces has to be equals to ma, the mass times the acceleration. But first, we need to get the sum of the forces. This is going to be vectors because that's the sum of the forces. So let's find what the sum of the forces are. Question tells us to say that we have two forces, F1 and F2. To make it easy for you to see, I will create a table the same way that you solve vectors. So I'll create a table here, and I will create two columns, one column will have the vectors themselves, and then the other two columns will have the components. You know, to say to add forces, we need to add them in component form. If the forces were just easy, like let's say like this, and maybe like this, we can easily add them because they are already in the same direction. So you can argue that these two forces are in the x-axis. Now, in this case, even though the question says horizontal, you have to see that horizontal, it can be that the table is something like this. This is how the table is. And by telling us that it is, these forces are acting in the horizontal direction, maybe what we have is the y-axis is maybe something like this, and the x-axis, let me just trace through. Maybe we have a situation where the x-axis is, the y-axis is that, and the x-axis is this. And then our object maybe is somewhere, we can even say that our object is somewhere here. So that the forces that are actually acting on this object will be the x component. Since I'm saying this is our x-axis, it will be that we have the x-axis there, the y-axis here. Let me make these red. Okay. One thing, then yes. Okay. So it can be that we have the x component as something like this, and then the y component as something like this. So it can be that these are actually the forces acting on our table, such that on our block, such that the resultant force itself is this one, this F1. By telling us to say that they are horizontal forces, they're just telling us to say that these forces are literally just pushing this object along this table. The object is not going up or it's not going down. So they're saying that we are in the X and Y, we don't go in the Z. But it doesn't necessarily mean that it has to be horizontal, the way we use horizontal to mean that it has to be to the left or to the right. It doesn't necessarily mean that. And it is clear based on the fact that the forces have, or the force F1 actually does have two components, the X and the Z, the X and the Y, I mean. With that in mind, let's look at the force F1. F1 is given to us, and we're given this. I think I did copy it, so let me just get it. Okay, this is our force F1. The best thing about this way of presenting vectors is there's no need for me to start getting the X component, the Y component. From here, I'll just get a 3. So from here, the X component is a 3. So I'll get a 3. No need for I. I was just telling me that I'm in the X axis. So then from the Y axis, the Y component, I have 4. So I've got that. But for F2, I know F2 will also be in this form. F2 will be such that I have F2 in X. I'll put I here, plus then I have F2 here as well, but in the Y axis, and I'll put J. This will be how F2 will look like. But since I don't know what it is, I'll put F2 in X here, and I'll put F2 in Y here. So this is what F2 will look like. I don't know what it is for now, but that's how it will look like. And then lastly, we are supposed to get the resultant force now. The resultant force will be the net force of these two. So of course, we know to say to get the net force is just the sum. In this case, it will be 3 plus F2 times the F2x, and then here it will be 4 plus F2y. This is how we are going to get the net force in this case. Once we get these, the forces, the net force here, the next thing will just be to get its magnitude and then work out the rest. So But before we even go to the last part, I think the question actually does give us what we need. It gives us what we need. So look at A, for example. In A, what are they saying? Find the acceleration of the chopping block in unit vector notation when the force F2 is equals to this. So in this case, they're saying F2 is equals to minus 3I plus minus 4. Of course, let me just put units there. Minus 3I minus 4J. So we're looking for the acceleration if that is what F2 is. So since they've given us what F2 is, there's no need for us to actually use X and F2X and so on. We can just get this here. For A, we see that F2X will just be minus 3. So while there's F2X here, I'll put minus 3. While there's F2Y here, I'll get this minus 4. So I'll put minus 4 here. Notice that when I add this, when I put minus 3 here, now I have 3 minus 3, and you should see that this whole lot here will just be a 0. So 3 minus 3, the net force will be 0. And then here as well, we're seeing 4 minus 4, the net force here will also be 0. So what are we seeing then? The sum of the forces, which is equals to MA. We've just seen that if F2 is equals to this expression, then the net force will be 0. If the net force is equals to 0, this is also equals to MA. We know the mass is not 0. Why? Because the question tells us what the mass is. The mass is 2 kg. That's the mass of the chopping block. So since the mass is known to be 2 kgs, it implies that what actually is 0 has to be acceleration. So the acceleration is equals to 0. If you really want to write 0 also in vector notation, then you have to write 0 in the I plus 0 in the J. But 0 is 0. There's no need for you to stress like this. Okay, so that answers the first part. Any questions? Okay, so that answers the first part. Let's look at B. What is happening in B? Well, it's the same setup, the same question. The only thing changing is what F is, F2 is. We're still finding acceleration, but now F2 is equals to minus 3 newtons in the I direction plus 4.0 newtons in the J direction. Again, find the acceleration. Okay, so remember how it goes. I'll still just get this table. You don't need to use this table, by the way. You can still just go directly. I just want you to get accustomed to say that I'm getting these components and this is how I'm using them. So in this case, F2 has these components. We're not touching F1. It's F2 that we're playing with. So I'll remove this. The resultant will also change. But for F2, the X component, we're seeing it is minus 3 still. The Y component is now positive 4. The difference is now the Y component is a positive 4, not a minus. So from here, we see that the resultant force will have components. The X component will be a 0. The Y component will be 8 when we add these two. So this will be 8. So that in the end, the sum of the forces will have 0 in the I direction, but it will have 8 in the j direction, this is how the force will look like. Once you have the force, you can then go back to Newton's second law. The sum of the forces is equals to ma. The question asked us to give the answer in unit vector form. Because of that, there will be no need for us to get the magnitude here, because if we were to use Pythagoras and so on, of course here Pythagoras will still just give us 8. But even if this was another number, there would be no need for us to combine this to get what F is. So here we'll just say that, okay, the sum of the forces, which is 0I plus 8J, will be equals to the mass, which is 2 kg, multiplying the acceleration, which is A. So from here, divide both sides by 2. By 2, it falls off here. So the acceleration will be 0. We know that will just be 0. So it will be 8J over 2, which will be equals to 4J. This is acceleration. So I can even do this so that I can just put my units as meters per second squared. You can use it like this, or if you wanted to use the setup that they are using, you can write 4 meters per second squared, and then in brackets, put the unit vector, J there. This would still be okay. Okay, so that answers B. I hope you guys are getting the hang of it now. Let's look at C. C, that's saying F2 is equals to 3.0 newtons, I, plus minus 4.0 newtons, J. So what will happen there? So this is now C. Again, but at this point, you should get how it's working. You don't have to keep doing the table and so on. You can do this without the table, because you saw that it's the resultant force that comes. Perhaps I should maybe even use the shortcut myself. This will actually just be the sum of the components. So I can say that, okay, from F1, what is my x component? F1 has x component 3, so I'll have 3 here, because I know its sum of forces equals to ma. My m is a 2. My a is what I'm looking for. It's a vector, so I can do that. And then this is where I'm doing a lot of work. The sum of the forces. From F1, I have 3 in the x, plus, how about from F2, I have 3, positive 3. So I'll say 3 plus 3. This is in the x-axis, so I'll put an I there. Plus, how about the other side? From F1, in the x-axis, I have a positive 4. So I'll say, from F1, I have a 4, plus, from F2, what do I have? I have a minus 4. So I want to say plus minus 4. This is in the J. When I reduce, this becomes a 6I. If you need units, you know this is a force due, so you can still have a Newton there. Then plus, this becomes 4 minus 4, which is 0J, is equals to the acceleration. So that this 0J just disappears, so that you have 6I is equals to 2, the acceleration there. So the acceleration in the end, when you divide both sides by 2, will just be equals to 3. If you need the units, this is acceleration, so I'll say meters per second squared, and then I'll put the unit vector I. It looks weird like this. In most cases, I would write this as 3I, and then I'll do this, and I'll put the unit vector, the units outside. But I'm just writing both because depending on the book you're using, sometimes they'll present it like this, sometimes they'll present it like this. If let's say both sides survived, as in even the J component survived, we would have had the acceleration being equal to maybe 3I plus 4J. And then I can do this and put the units meters per second squared outside, if I'm using this notation. Or we could have even had something like 3 meters per second squared, and then an I here, then plus 4 meters per second squared, and a J here. That is if both would have survived, the X component and the Y component. But for these examples, only one component was surviving, So we were ending here. Okay, so any questions up to here? Okay, let's look at the second one. If the 1 kg standard body, if a 1 kg standard body has an acceleration of 2 meters per second squared at 20 degrees to the positive direction of an x-axis, what are A, the x component, B, the y component of the net force acting on the body, and C, what is the net force in the unit notation? Okay, so and again something easy. But it all depends on how we understand this question. If we fail to understand the question, we are going to struggle to answer this question. Okay, so what are they saying? We have a 1 kg standard body. So the standard part just there to confuse us. So this is just a 1 kg object. So you have a 1 kg object here that has an acceleration of 2 meters per second at 20 degrees to the positive x direction. So let's look at it. If the positive x direction is something like this, so that the positive y is something like this, then this body has an acceleration of 2 meters per second. I'm guessing this is 2 meters per second squared, because we know those are the units for acceleration. So an object has that acceleration, but this acceleration is at an angle to 20 degrees from the positive x-axis. So the angle here is 20 degrees. Now, what are the x components and y components of the net force acting on the body? Well, what do we know? Well, here's the thing. From Newton's second law, let me just go through it one more time. Newton's law predicts that the acceleration of a body, A, will be directly proportional to the force that is causing it, but inversely proportional to the mass. You can think about it like this, or even better, I like to just think of it as just these two. What causes the acceleration is actually just that force there. This is how it goes. Now, what this implies is that the force is the one that creates the acceleration. And the direction of the acceleration is the same as the direction of the force. If you find that the force is negative, then it implies that the acceleration will be in the negative direction. But all what I'm trying to say here is that if this object experiences a force like this, you can't see it accelerate in that direction. It will accelerate in the direction of the force. The acceleration is always in the direction of the force. What does that imply? It then means that in our case, where the acceleration was in this direction, 20 degrees to the horizontal, even the force was in that same direction as well. I hope you're getting that. So the force and the acceleration are in the same direction. So in the same way that the force can have components, even the acceleration will also have components. We so to say, the force can be broken into two components, the x-axis and the vertical axis. Well, acceleration is also a vector. It can also be broken into an x component and a y component. So let's look at force first. So we know to say for our case, we have a 20-degree angle here. So the net force here is the one that actually causes that acceleration. So the acceleration, the question gives us to say it's a 1 kg object that is given an acceleration of, let's check that acceleration again. A 1 kg object that is given an acceleration of, where is that? 2 meters per second squared. So this force, the net force here, it's the one that is creating this MA. Since the M is 1, so I can say this is 1 times 2. So this will just be 2 newtons. This is what the net force is. Now, having found the net force, now the question is not asking us for the net force. Instead, it's asking us to find the components of the net force. So since we've just seen that the net force ends up being 2 newtons, now we can easily determine what its components will be based on what the original force will be. So the X component is here, as we saw earlier. The Y component is here. The 20 degrees is here. So you can then say the X component, remember how we get components? The X component is side by side with the angle. So we're using cos there. So I'll say Fx is equals to the, I've identified the cos there. So it's the vector itself, which is 2. Then cos, which is the ratio I've identified. Then the angle I was comparing with, which is 20 degrees. This is what will give me the X component. To get the Y component, I see it is opposite to my angle there, so I use sine. So the Y component will be equal to the vector itself, which is 2, the force, the ratio I've identified, which is sine, then the angle I was comparing with. So this is what I'll be evaluating. So what will be Fx? What will this be? 1.879. How about the Fy? 0.684 newtons. Okay, so you can write this also to 3 significant figures, which becomes 1.88 newtons. These become the 2 components for our force. The second part of the question was asking for what? In the second part, they're saying, where is that here? Oh, found that's A, the X component, B, the Y component, and C, what is the net force in unit notation, unit vector notation? Remember how unit vector notation goes? Just like in the previous case, they are asking us to express that net force, F net, in the form Fx in the I plus Fy in the J. We already have what these are. Fx is 1.88, so just say 1.88 here. I plus Fy is 0.684. The 0.684 J. So we can write it like this, and then we can put the units outside here and say this is in newtons. Or we can say 1.88 newtons in the I direction plus 0.684 newtons in the J direction. We can write it like this, or we can write it like this. Okay, so any questions so far? Okay, so yeah, these are the questions that we are seeing here. They are nice, not very complicated, but they seem interesting. Okay, what else are we seeing here? I'm trying to see if we can do one more. Anything that doesn't take us too much time. Okay, so I'm seeing question 3 seems to be a little bit long. So it seems a little bit long. I can record this and then share it with you guys later on. So in the meantime, let's move on to look at question 4. Seems to be very, very short. I think we can do it. Let me see if it's something that you guys can do or we can do together. A 2 kg infant is subjected to 3 forces that give it an acceleration of this. See this? Unit vector, unit vector. So they're using that unit vector notation form. If three of the forces are F1 is that, F2 is this, find the third force. If two of the three forces, so they've given us F1, they've given us F2, but this infant is subjected to three forces. So find the missing one. Okay, so yeah, this is this question. They've given us the acceleration, they've given us the mass of the infant. Would you guys want me to work out this question for you guys now? It should be a 5-7 minutes thing, or you guys can pull it off later on. What do you guys think? Okay, so let me ask you guys to try out question 4. Send in the group what you find. You can send in the group, or you can share it with me. If you guys struggle, I can still record it for you and share it with you guys. Yeah, so let's end here. Let's do more tomorrow, and then whatever is missing, I will record and upload for you guys. So tomorrow we're going to look at some more interesting ones, and we're going to concentrate mainly on the last few days on here. So let's do this tomorrow night.